In early 1943, the Atlantic Ocean was the most dangerous place on Earth. Not a battlefield you could see, not a front line drawn on a map, just thousands of miles of cold, black water, and beneath it, something hunting. German U-boats. They were long, narrow submarines designed not for fair fights, but for ambush. They waded along shipping lanes like wolves in tall grass. At night, they surfaced, running on diesel engines, faster and more maneuverable than the convoys they stalked. When they attacked, it was sudden. A torpedo streaked through the darkness, then another, then another. Merchant ships carrying fuel, ammunition, food, and soldiers erupted into fire. Survivors struggled in freezing water that could kill in minutes. By 1942, the situation had become catastrophic. The United States had just entered the war after Pearl Harbor. Britain depended entirely on transatlantic shipping for survival. Every tank, every aircraft part, every loaf of bread had to cross the ocean, and the ocean belonged to the U-boats. German Admiral Karl Dönitz believed he could win the war in the Atlantic alone. His strategy was simple: sink ships faster than the Allies could build them. He deployed coordinated wolf packs, groups of submarines that spread out across vast areas, radioing one another when they spotted a convoy. At night, they attacked together, overwhelming escorts. Convoys burned while submarines slipped away into darkness. The numbers were terrifying. In 1942 alone, over 1,000 Allied ships were sunk. Along the American East Coast, oil tankers exploded within sight of shore. The sea glowed with flames. Civilians watched from beaches as silhouettes of burning ships marked the horizon. The Allies were not defenseless. Destroyers and corvettes escorted convoys. Aircraft patrolled overhead when weather allowed, and when a submarine was detected underwater, ships dropped depth charges, heavy steel barrels filled with explosives set to detonate at a specific depth. But depth charges were blunt instruments. To use them, a ship had to know almost exactly where the submarine was. Sonar could estimate position, but once the attack run began, contact was often lost. The destroyer passed over the target and rolled explosive barrels into the sea. They sank silently. Seconds later, massive underwater blasts shook the ocean. Sometimes they worked. Often they didn't. A U-boat captain could change depth, alter course, cut engines, or hide in thermal layers where sonar reflections weakened. Explosions would thunder nearby, lights would flicker, bolts might loosen, but the submarine survived. And when the escorts ran out of depth charges or lost contact, the hunter became the hunted again. Statistics told a brutal truth. On average, it took dozens of depth charges to sink a single submarine. Many attacks damaged nothing at all. Aircraft faced an even greater challenge. If a plane spotted a U-boat on the surface, the submarine could crash dive in less than 30 seconds. By the time bombs or depth charges hit the water, the target was already slipping away into the deep. The core problem was simple and devastating. Once a submarine disappeared beneath the surface, the ocean swallowed it. The Allies needed something radically different. Not a bigger explosion, not more ships. They needed a weapon that didn't guess where a submarine might be, but followed it. The idea sounded almost impossible. What if a weapon could hear? Submarines made noise. Even underwater, they were not silent. Propellers churned water, electric motors hummed, machinery vibrated against steel hulls. To human ears above the surface, the ocean seemed mute, but underwater, it was alive with sound. Scientists had been studying underwater acoustics for years. Hydrophones could detect distant ships, sonar pulses could bounce off hulls, but detection was only half the battle. The real challenge was guidance. How could a weapon adjust its course after entering the water? In December 1941, just days after the attack on Pearl Harbor, the United States quietly began exploring an answer. At institutions like Bell Telephone Laboratories and Harvard's Underwater Sound Laboratory, physicists and engineers were asked to attempt something unprecedented: build a self-guiding anti-submarine weapon. It had to be small enough to drop from an aircraft, it had to survive impact with the ocean, it had to function autonomously, and most importantly, it had to detect and chase the sound of a submarine's propellers without human control. The timeline was brutal. Ships were sinking every week. There was no luxury for slow experimentation. The project was pushed forward with urgency bordering on desperation. Meanwhile, the Battle of the Atlantic intensified. Convoys crossing from North America to Britain sailed through what sailors called the air gap, a vast stretch of ocean beyond the protective range of land-based aircraft. In that gap, U-boats hunted with near impunity. Escorts fought back fiercely, but losses mounted. Every sinking meant lost supplies, lost time, and lost lives. By 1942, the Atlantic campaign stood at a tipping point. Allied shipbuilding capacity was increasing, but so were submarine patrols. Intelligence breakthroughs like code breaking were helping, but they were not enough on their own. The war at sea demanded a technological leap. Some within Naval Command doubted the feasibility of an acoustic weapon. Electronics were fragile. Vacuum tubes were sensitive. Salt water corroded everything. The ocean was a violent, chaotic environment. Could delicate listening equipment really survive being hurled from an aircraft and plunged into cold, turbulent water? But others understood the stakes. If a weapon could pursue a submarine after it dived, if it could turn toward noise, correct its path, and continue tracking, it would transform anti-submarine warfare. Instead of guessing, instead of saturating the ocean with explosives, instead of hoping, it would hunt. And somewhere in laboratories far from the crashing waves of the Atlantic, engineers were racing to make that impossible idea real. They would disguise it under an innocent name. They would call it a mine to conceal its true nature. No photographs would be released. Its existence would be classified at the highest level. Even many Allied sailors would never know what had changed. But before it earned a name, before it claimed its first target, before U-boat commanders realized something new was stalking them in the deep, there was only a crisis, an ocean full of wolves, and the desperate need for a weapon that could listen in the dark. In December 1941, while American battleships still burned at Pearl Harbor and the United States scrambled to mobilize for a global war, a small group of scientists received an unusual assignment. The Navy did not ask them to build a bigger bomb. It did not ask for faster ships. It asked for something that sounded almost like science fiction. Build a weapon that can think underwater. The problem was clear. Submarines vanished the moment they dived. Depth charges were guesses wrapped in steel. Aircraft attacks depended on perfect timing. Once a U-boat slipped beneath the surface, the advantage shifted instantly to the hunter below. What if that advantage could be reversed? The concept being proposed was radical: an air-dropped weapon that would enter the ocean, activate itself, listen for the sound of a submarine's propellers, and steer toward it automatically. No wires, no remote control, no human guidance. Once released, it would be alone in the dark. Responsibility for this extraordinary project fell to a coalition of American scientific powerhouses. Bell Telephone Laboratories brought expertise in electronics and signal processing. Harvard's Underwater Sound Laboratory contributed cutting-edge research in acoustics. General Electric would eventually help translate delicate laboratory designs into reliable production hardware. The effort was overseen by the National Defense Research Committee, which had already been coordinating secret wartime science initiatives. The urgency was absolute. Ships were sinking faster than they could be replaced. The Atlantic was bleeding. From the beginning, the weapon faced brutal constraints. It had to be light enough to carry beneath aircraft like the consolidated B-24 Liberator. It had to survive a drop from several hundred feet without breaking apart. It had to function in freezing salt water. And it had to operate using electronics that, at the time, were bulky, fragile, and heavily dependent on vacuum tubes. Transistors did not yet exist. Everything depended on glass tubes glowing with heated filaments. Inside laboratories, engineers began solving one problem at a time. First, propulsion. The weapon needed its own motor, quiet, reliable, powerful enough to drive it through water at a useful speed. They selected an electric motor rated at approximately 7.5 horsepower. Electric propulsion offered two advantages. It produced less noise than combustion engines, and it eliminated exhaust bubbles that could disrupt acoustic sensing. Next came the ears. Hydrophones, underwater microphones, were arranged to detect sound directionally. The principle was elegantly simple in theory, but fiendishly complex in practice. If sound from a submarine's propellers reached one sensor slightly stronger than another, circuitry could interpret that difference and adjust control surfaces to steer toward the louder signal. In other words, the weapon would turn toward noise. The guidance system relied on vacuum tube amplifiers and analog circuitry built from components similar to those found in telephone switching systems. Bell Labs engineers were masters of signal processing. They adapted knowledge originally intended for routing long-distance calls and filtering static into a weaponized acoustic brain. But underwater acoustics are not clean. The ocean is filled with echoes, temperature gradients, surface noise, and biological sounds. Waves slap the surface, ships churn above. Even the weapon's own motor created interference. The team had to ensure it would not chase random noise or circle aimlessly. One solution was to tune the device to the specific frequency range produced by submarine propellers. German U-boats generated characteristic acoustic signatures when running submerged on electric motors. By filtering out irrelevant frequencies, the weapon could focus on its intended prey. Then there was the question of durability. When dropped from an aircraft, the weapon would strike the water at high speed. If it hit at the wrong angle, it could tumble or break apart. Engineers designed a short, compact body, about 2 feet in diameter and roughly 7 feet long, shaped to stabilize quickly after impact. It was intentionally fat compared to traditional torpedoes, improving hydrodynamic stability at moderate speeds. Testing began under intense secrecy. Early prototypes were dropped into controlled waters while researchers monitored performance. Failures were common. Electronics short-circuited, components flooded, guidance systems locked on to the wrong sounds. Every flaw meant more redesign, more sleepless nights. Yet progress moved with astonishing speed. In less than a year, the project advanced from theoretical sketches to working prototypes. On December 7, 1942, exactly 1 year after Pearl Harbor, one of the first successful tests took place. The symbolism was not lost on those involved. What had begun in the aftermath of catastrophe was becoming a functional weapon. Secrecy surrounded everything. The Navy feared that if Germany discovered the existence of an acoustic homing torpedo, countermeasures would follow quickly. Submarines could deploy noise-making decoys. Engineers could modify propeller designs. The advantage would evaporate. So, the weapon received an intentionally misleading name, the Mark 24 mine. It was not a mine at all. Mines sit and wait. This device hunted. Even within Allied forces, knowledge was compartmentalized. Air crews trained to deploy it were given minimal technical explanation. They were instructed on release altitude, speed, and safety procedures, not on how the weapon actually worked. Few understood that once it entered the water, it began listening. By early 1943, production ramped up. General Electric translated laboratory builds into standardized units suitable for wartime manufacturing. Each device cost roughly $1,800, a modest price compared to the fuel, time, and ammunition wasted in unsuccessful depth charge attacks. The weapon's internal architecture was a marvel of compact engineering. A battery provided power. The motor drove twin propellers. Hydrophones fed signals into vacuum tube amplifiers. Control circuits adjusted rudders automatically.
and at the front, a warhead waited. Not enormous, but sufficient. It did not need to break a submarine in half. A well-placed detonation could rupture pressure hulls or disable propulsion, sealing a U-boat's fate. One design decision was especially clever. The torpedo was programmed not to detonate immediately upon first detecting noise. Instead, it would circle and reacquire if it overshot, increasing the chance of a lethal strike. This behavior gave it a persistence depth charges lacked. As units left the production line in March 1943, they represented something entirely new in warfare. Not just a better bomb, but a primitive, autonomous system. It sensed its environment, it processed information, it adjusted its course without human intervention. Inside laboratories, engineers understood they had crossed a threshold. For centuries, weapons had traveled in straight lines, guided only by gravity or initial aim. Now, for the first time in operational history, a widely deployed munition could actively seek its target after launch. Yet no one outside a tight circle knew. There were no press releases, no photographs, no public acknowledgement. The crates were labeled blandly. Documents were classified at the highest levels. If a unit malfunctioned or failed, rescue teams moved quickly to prevent capture. Some German submariners would later report strange experiences, explosions that seemed to follow them, impacts that felt too precise to be random. But in early 1943, they had no idea such a device existed. The scientists who built it could not boast of their success. Many would remain anonymous for years. Their invention would not appear in wartime propaganda. It would not be celebrated in newsreels. Instead, it would slip quietly into the Atlantic aboard patrol aircraft. And soon, somewhere over cold gray water, an aircrew would release one. For the first time in naval history, a submarine would dive, and something would dive after it, listening.
May 12, 1943. The North Atlantic was gray, restless, and unforgiving. Low clouds pressed down over cold water as an aircraft from RAF Coastal Command cut across the sky on routine patrol. The aircraft was a consolidated B-24 Liberator, flying with number 86 Squadron, scanning the vast emptiness below for a shape that rarely wanted to be seen. Below the surface, somewhere, German submarine U-456 was returning from patrol. Like many U-boats that spring, it operated in a shrinking zone of safety. The tide in the Atlantic War was beginning to turn, but no one in that moment could feel the certainty of it yet. From the air, the first sighting was sudden. A dark silhouette on the surface, a narrow hull slicing through water. For a few seconds, the submarine and the aircraft shared the same world: wind, waves, daylight. Then the alarm sounded below decks. Flugzeug, aircraft. On the submarine, the order to crash dive came instantly. Crewmen moved with drilled precision. Hatches slammed shut, ballast tanks flooded, the bow angled downward, diesel engines cut, electric motors engaged. In less than half a minute, U-456 began slipping beneath the surface, trading speed for invisibility. This was the moment that usually saved them. For years, the pattern had repeated itself. Aircraft spotted submarine, submarine dived. Aircraft dropped depth charges, hoping to guess the right position and depth. Explosions shook water, but most submarines survived by maneuvering in 3 dimensions, disappearing into the ocean's acoustic confusion. The Liberator's crew had made these attacks before. They knew how quickly a U-boat could vanish, but on this day, they carried something different beneath their wings. Not a string of depth charges, a single compact weapon labeled mine. Inside the aircraft, the release sequence began. Speed, altitude, angle, everything had to be correct. Too high, and the weapon might break on impact.
too low, and the aircraft risked flying directly over anti-aircraft fire if the submarine surfaced again. Below, U-456 was descending. Water pressure creaked against the hull. Inside, men listened for the familiar thunder of exploding depth charges. Instead, the sea received a short, blunt torpedo. It struck the water and disappeared. For a moment, there was nothing. No explosion, no immediate shockwave, just cold Atlantic water closing over steel. Then, beneath the surface, the weapon came alive. A battery engaged. The electric motor began turning twin propellers. Inside its sealed compartment, vacuum tubes glowed faintly as circuitry powered up. Hydrophones opened their silent ears to the ocean. And the ocean was not silent. Even running submerged on electric motors, a submarine could not erase its acoustic signature. Propeller blades churned water, creating rhythmic pulses. Mechanical systems vibrated through metal. In the stillness below the waves, those sounds carried. The weapon detected them. Unlike a depth charge, it did not fall blindly. It began to swim. Its guidance system compared sound intensity across sensors. If the signal was stronger on one side, control surfaces adjusted slightly, nudging it toward the source. Above, the Liberator circled, the crew watching for signs of oil, debris, or a resurfacing hull. They had little direct control now. The outcome was unfolding underwater, beyond human sight. Inside U-456, tension thickened. Sonar operators listened. The usual pattern after an air attack involved bracing for concussions, explosions somewhere above or astern. But this was different. There was movement. Reports from later encounters described it as something uncanny, an explosion that did not feel random, a detonation that seemed to follow. The acoustic torpedo closed distance steadily. It was not exceptionally fast by later standards, but it did not need to be. It only needed to be persistent. If the submarine turned, the sound shifted. The torpedo adjusted. If the submarine tried to change depth, the propellers still produced noise. The signal remained. Some accounts suggest U-456 attempted evasive maneuvers, hard turns, changes in speed, but every maneuver generated more acoustic information. In the dark water, the weapon continued homing. Then the detonation came. A sharp underwater explosion struck the submarine, not the distant concussive pattern of depth charges, but a direct hit. Steel ruptured, systems failed, flooding began. Damage reports cascaded through the compartments. U-456 was mortally wounded. The submarine did not sink instantly. Historical records show that it was heavily damaged and later finished off, but the attack marked a turning point. For the first time in operational combat, an air-dropped acoustic homing torpedo had successfully struck a German U-boat. Above, the aircrew saw signs that confirmed severe damage, oil slicks, debris, the subtle but unmistakable indicators that the ocean had claimed another submarine. They couldn't fully appreciate what had just happened. This was not merely another successful patrol. It was proof of concept under fire. The weapon had worked, not in a controlled test range, not against a cooperative target, but in the chaotic reality of war. Word traveled quickly through Allied command channels. Reports were analyzed carefully. Performance data was scrutinized. The conclusion was undeniable. The new device had achieved something depth charges rarely did with such efficiency. In the weeks that followed, more deployments occurred. Air crews learned how to position themselves for optimal release. Tactics evolved. Instead of saturating an area with explosives, aircraft could now drop a single homing weapon once a submarine began to dive. The psychological impact on German crews began subtly. Some captains reported that explosions seemed unusually accurate. Others suspected improved sonar coordination or better trained escorts. They did not yet imagine a weapon that could independently track them underwater. That ignorance was crucial, because the Mark 24, still officially called a mine, depended on secrecy as much as technology. If Germany realized that acoustic homing torpedoes were in use, countermeasures might follow: noise decoys, mechanical noisemakers, modified propulsion techniques. But in mid-1943, such defenses were not yet deployed widely against this threat. The Battle of the Atlantic was entering its decisive phase. Allied convoy systems were tightening. Long-range patrol aircraft were closing the air gap. Intelligence from code-breaking efforts was improving routing, and now aircraft possessed a weapon that did not merely frighten submarines into diving, it punished them for it. For years, the submarine's crash dive had been its shield. On May 12, 1943, that shield cracked. Somewhere beneath the gray Atlantic, a torpedo had listened in the dark and found its mark. And from that moment on, every U-boat captain faced a new uncertainty. When you dive to escape the sky, what if something dives with you?
By the summer of 1943, something had changed in the Atlantic, and German submarine crews could feel it, even if they could not explain it. For years, aircraft had been a threat only while a U-boat remained on the surface. The moment a crash dive was executed, survival odds improved dramatically. Depth charges were terrifying but survivable. Explosions might rupture pipes, crack gauges, or injure crewmen, yet most submarines escaped after enduring the barrage. Now, reports filtering back to German command described something different. Attacks that did not feel random, explosions that came too close, damage that suggested precise underwater tracking. The Allies, meanwhile, were studying numbers with growing confidence. After its first operational use in May 1943, the Mark 24 acoustic weapon, still officially labeled a mine, was deployed more widely by U.S. Navy and RAF Coastal Command aircraft. Each engagement was documented carefully. Analysts compared outcomes to traditional depth charge attacks. The results were striking. Out of 204 confirmed launches during the war, 37 submarines were sunk and 18 more damaged. That represented a kill rate of roughly 18%. By comparison, depth charge attacks from aircraft averaged closer to 9.5% effectiveness under similar conditions, nearly twice as effective. In a war measured in shipping tonnage and patrol attrition, that difference mattered enormously. Every submarine destroyed meant fewer torpedoes launched at convoys. Every damaged boat forced weeks or months in dry dock. And by 1943, Germany could not replace losses as easily as before. Production plans had originally envisioned as many as 10,000 units, but as the weapon proved effective and the strategic tide turned, the order was reduced to approximately 4,000. It was not a weapon meant for saturation, it was a precision tool, deployed when conditions were right. The secrecy surrounding it remained absolute. There were no wartime photographs released to the public, no celebratory announcements. Even many Allied sailors believed they were still using improved depth charges rather than something fundamentally new. Captured German records later revealed a telling detail. They never fully understood what had hit them. There were suspicions. Some commanders theorized that the Allies had improved sonar coordination or developed better timed fuses, but the idea of a self-guiding acoustic torpedo dropped from aircraft did not solidify into confirmed intelligence during the critical period of 1943. As a result, effective countermeasures were delayed. Noise decoys, devices designed to lure acoustic torpedoes away from submarines, would later become standard in naval warfare. But against the Mark 24 in 1943, U-boats often faced it unprepared. When they maneuvered aggressively to evade attack, they increased propeller noise. When they attempted to accelerate, they amplified the very signal guiding the weapon toward them.
The more urgently they tried to escape, the clearer they became. One of the most dramatic demonstrations of the weapon's reach occurred far from the North Atlantic convoy lanes. In June 1944, the Japanese submarine I-52 was crossing the Atlantic on a secret Yanagi mission, an exchange voyage between Japan and Germany. On board was a cargo of strategic materials, including rubber, tin, and reportedly a significant shipment of gold intended as payment for German technology. The voyage was clandestine and perilous. Allied codebreakers had intercepted communications that revealed I-52's route and rendezvous plans. An American escort carrier group, including aircraft equipped with acoustic torpedoes, was dispatched to intercept. When contact was made, the submarine attempted to evade as any experienced crew would. It submerged, it maneuvered, it trusted in depth and darkness. But this was no longer enough. An aircraft dropped acoustic torpedoes into the Atlantic. One of them acquired the sound of I-52's propellers. It homed in beneath the surface and detonated. The submarine was lost with all hands, along with its valuable cargo. Decades later, sonar recordings from that attack, captured using sonobuoys, would survive in the U.S. National Archives. They preserve the eerie acoustic signature of a submarine's final moments, a haunting reminder that the ocean remembers sound long after ships disappear. By the end of the war, the Mark 24 accounted for approximately 15% of all German U-boats destroyed by aircraft. That figure is remarkable considering how few were launched relative to conventional munitions. It was not deployed carelessly. Air crews were instructed to use it only when a submarine was confirmed and diving, ensuring maximum probability of success. The weapon was too valuable and too secret to waste. Financially, it was efficient as well. At roughly $1,800 per unit, it was less costly than the cumulative expense of repeated failed depth charge runs, not to mention the fuel and operational risk involved in prolonged attacks. Strategically, its timing was critical. In the spring of 1943, German U-boat losses began to climb sharply. That period, often called Black May by the Kriegsmarine, saw devastating attrition rates. Multiple factors contributed: improved radar, expanded air coverage, code-breaking intelligence, and better convoy tactics. But among those factors was a weapon that hunted silently after the crash dive, removing the submarine's most reliable defensive move. And yet, throughout the war, its existence remained cloaked. Documents were classified at the highest levels, technical details were compartmentalized. Even post-war summaries initially referred to it cautiously. The designation Mark 24 mine persisted, a bureaucratic disguise concealing a technological leap. German naval engineers, had they known earlier, might have accelerated acoustic countermeasure development. They eventually produced decoys like the Bold device, designed to create noise bubbles and confuse sonar. But widespread, effective acoustic decoys tailored specifically against the Mark 24 came too late to neutralize the Mark 24's early advantage. By the end of the war in 1945, the Battle of the Atlantic had shifted decisively in favor of the Allies. Convoys flowed with far fewer losses. U-boat patrols became increasingly hazardous. Crews who once felt like apex predators found themselves hunted relentlessly. Behind that transformation stood many visible innovations: radar masts, escort carriers, long-range patrol aircraft, and one nearly invisible one, a short, compact weapon built from vacuum tubes and telephone components, a device that listened instead of guessing, a torpedo officially called a mine, so secret that no wartime photograph was ever released. It did not win the Atlantic War alone, but in the dark calculus of tonnage, attrition, and survival, it shifted probabilities. It narrowed escape margins. It forced submarines to fear the deep itself. Because after 1943, diving no longer meant safety. It meant entering a world where something might already be listening.
When the war ended in 1945, many of the technologies that had shaped it were revealed to the public in photographs, parades, and headlines. Radar stations, jet aircraft, rocket missiles, the atomic bomb. The Mark 24 was not among them. It slipped quietly into declassified reports and technical archives, overshadowed by larger, more dramatic weapons. There were no iconic images, no dramatic footage of launch and impact. For years, even its existence remained obscure outside naval circles. And yet, in a deeper sense, it marked the beginning of something far more enduring than a single wartime advantage. For centuries, weapons had followed simple physics. An arrow flew along a predictable arc, a cannonball traveled in a straight line. Even early torpedoes ran on preset gyroscopic courses. Once launched, they did not adapt. If the target moved, the shot missed. The Mark 24 changed that equation. It sensed, it processed, it adjusted. In doing so, it became one of the first operational smart weapons, a munition capable of autonomous guidance after release. It did not require a human operator with a joystick. It did not receive radio commands. It interpreted its environment using onboard sensors and analog circuitry, making real-time decisions based on acoustic input. This was not artificial intelligence in the modern sense, but it was a clear step toward autonomous targeting. Naval strategists understood the implications immediately. Submarines had long relied on stealth and maneuverability to survive. If weapons could track them based on sound, then silence would become paramount. The underwater battlefield would transform into a contest not just of firepower, but of acoustic signature management. After the war, development accelerated. The U.S. Navy refined acoustic homing torpedoes into more advanced models. Guidance systems became more sophisticated. Vacuum tubes gave way to transistors in the 1950s, reducing size and increasing reliability. Passive and active sonar technologies expanded dramatically. By the early Cold War, submarines were no longer diesel-electric boats operating primarily near the surface. Nuclear propulsion allowed them to remain submerged for months. But nuclear reactors introduced new acoustic challenges. Machinery noise had to be dampened. Hull designs were reshaped to reduce hydrodynamic turbulence. Silence became survival. The legacy of the Mark 24 echoed through this evolution. It had demonstrated that a weapon could exploit sound as a tracking mechanism. From that point forward, submarine designers and anti-submarine engineers were locked in a technological duel, quieter submarines versus more sensitive sensors. Modern torpedoes, such as those deployed during the late Cold War, incorporated active sonar, passive acoustic homing, wire guidance, and sophisticated counter-countermeasure algorithms. They could discriminate between targets, ignore decoys, and re-attack if they missed. All of that traced back to a modest device built in 1942 from telephone components and vacuum tubes. The concept extended beyond naval warfare. Guided munitions in air and land combat followed similar principles. Heat-seeking missiles tracked infrared signatures. Radar-guided missiles followed reflected radio waves. Later systems incorporated laser guidance and satellite navigation. Each represented a shift away from unguided explosive force toward precision engagement. In that sense, the Mark 24 belonged to a lineage that would eventually include cruise missiles and precision-guided bombs. It proved that autonomy, even in primitive form, was not only possible, but decisive. There were ethical dimensions as well. When a weapon makes adjustments on its own, even through simple analog logic, responsibility becomes layered. The human decides when to deploy it, but the final targeting corrections occur beyond direct human control. In 1943, this was a revolutionary idea. Today, discussions about autonomous weapons and artificial intelligence in warfare echo similar concerns, only amplified by digital complexity.
The Mark 24 operated on vacuum tubes and basic analog filters. Modern systems rely on microprocessors and advanced software. Yet the philosophical question remains: how much decision-making should be delegated to machines once a weapon is in motion? During World War II, survival left little room for debate. The Atlantic supply line was essential. Every submarine sunk meant fewer sailors lost in icy water. The urgency of total war justified innovation without public scrutiny. But history allows us to see the broader arc. What began as an emergency response to German wolf packs became a foundation stone for modern precision warfare. And still, the story remains strangely quiet. No famous wartime photograph captures its launch in heroic silhouette. It existed in secrecy, performed its task, and receded into technical documentation. Yet its impact was measurable. Out of just over 200 combat launches, 37 submarines were destroyed and 18 more damaged. Roughly 15% of all German U-boats destroyed by aircraft fell to this single class of weapon. At a cost far lower than repeated depth charge assaults, it increased efficiency and reduced risk to Allied air crews. More importantly, it altered the psychology of submarine warfare. Before 1943, diving meant relative safety from aircraft. After the introduction of acoustic homing torpedoes, diving meant entering a realm where sound itself could betray you. The ocean was no longer a shield, it was an acoustic battlefield. In the decades that followed, submarines grew quieter. Detection systems grew sharper. The underwater arms race intensified across oceans during the Cold War. Nuclear submarines stalked each other in silence, each aware that somewhere in the dark, sensors were listening. The silent hunter had become a permanent presence. The Mark 24 did not dominate headlines. It did not end the war alone. But it represented a turning point, the moment when a weapon first demonstrated that it could pursue its target by interpreting the environment, rather than relying solely on initial aim. In the cold waters of the Atlantic, a small, short, blunt torpedo proved that machines could listen, decide, and strike without further human guidance. And from that moment forward, warfare would never be entirely blind again.